So good afternoon, everybody. Welcome to this afternoon session, the first session today afternoon in this course on AI and ML opportunities, excellence opportunities in AI and ML for manufacturing. So this let me just share or this session will be an hands-on session. So Om Prakash is here with us. Om Prakash is a PhD student in chemical engineering department in the broad area of process control, and he will be taking you through a regression problem, okay, where you can see a regression in action. Before I hand over to him, is there any question based on what we did in the morning? Any questions, suggestions, comments again? If there are any questions or what was done earlier by Professor Goody or by Professor Sharad or me yesterday, any topic, any question you have or anything? Okay. If there are no questions or comments, I think we can start. So Om Prakash, can you?
Yes, sir.
Yeah. Thanks.
Yeah, I will share my screen.
Yeah.
Can you see my screen?
Yes, Om Prakash, we can see
Yeah.
your screen.
Okay. So hello everybody. We'll look at linear regression problem first. This is the paper I'll be following. Here, okay, I will just. Yeah. So here the objective is to predict some of the properties of biodiesel. So in biodiesel we have different kind of feed which are derived from different sorts of different kind of organic materials. Like we have soybean, sunflower, mustard biodiesels. So, and they have different kind of fatty acid composition. So these are okay. Sorry, this is a different table. Yeah. So these are my biodiesel, soybean, sunflower, and all. And these are my fatty acid compositions. Okay, lactic acid, stearic acid, oleic acid, and these are my weight percentage of the fatty acid in a particular biodiesel. Okay. So based on this data, we want to uh, predict our properties of the biodiesel, which are pour point, cloud point, fire point, etc. Okay. So this is the data given. Okay. And now if somebody give me some another vegetable oil whose uh, fatty acid compositions are known, then can I fit some curve so that can I predict the properties then? And if it is known that this fatty acid composition and the properties follow a linear relation, then can I predict the those properties? So this is my objective here. Okay. So I will just show you the code. So this is Octave. I hope you can see the Octave command window, and this is the editor. Yeah. So, here I have written these fatty acid compositions. So I had so I have 6 fatty acids, okay, and 10 different types of biodiesel. So uh, so I have these six type of fatty acid, and these are my biodiesels, okay, and so these are actually column vector, okay. So so in and here is one of the properties of the biodiesel, which is pour point. So I'll be fitting a straight line for this property pour point, okay. So So in the morning lecture, Professor Gudi showed us the ways how to fit a straight line for this linear regression problem. So you can do. There are two ways you can do that. There is a direct method in Octave or MATLAB. So where you can just uh, feed this X matrix, which is the uh, your uh, matrix whose column contains this fatty acid. Okay.
Sir, can you explain how to that is that Y matrix has been constructed, because X you are obtaining from the table, how you are
Yeah.
computing that Y value? That is
Okay. Yeah, I'll just show you.
okay.
So my Y values are given. Okay. So I am trying to fit 4 point. Okay. So these are my Y values. So these are given. Okay, -4. So these are 4 point. Okay, -4 degrees C. So this 4 point is given to me for different biodiesels. Similarly, I am given this data, my fatty acid composition for different biodiesel. Okay.
So I may add here, Prakash, just so when you say how Y was generated, no, this is experimental data.
This
So
is
when you did experiments, there you measured the Y. So for different types of vegetable oils, you measured their properties. So this is what in machine learning we will call as the training data.
Yes, sir.
Based
Yes, sir.
based on this data, now you fit a relation between
Yeah.
Y and X, like using several properties, you predict Y, and in future, you give me a new biodiesel for which you do not know the Y, but you know the X,
Yes,
and
sir.
I
I'll
will,
accept it. Previously, he
yeah.
didn't show this Y table. That's why I got
Yeah, yeah,
confused. Yeah,
yeah, yeah,
definitely.
yeah, yeah. So this is the training data is what we are looking at. Yeah,
Okay.
thanks. Yeah,
yeah.
Thanks, sir.
thanks for asking. So it got clarified. Yeah,
Yeah. So this is
yeah.
my
Okay,
Y.
go ahead. Yeah.
Yeah. So this is my Y data and this is my X data. So I'll construct this matrix. I have constructed this X matrix where my rows are my biodiesel, my vegetable oil, and these columns are my fatty acids. Okay. So this is my X. So in linear regression, you know that there is a constant term. Okay. So this is the linear regression model which we are trying to fit. Okay. So Y is the property, which in this case is 4 point, and then these are the parameters. Okay. So A0 is constant here, and similarly we have A1 to A6, and X1, X2 are the fatty acid compositions. Okay. So so, so you see, a note is constant. So corresponding to this, we have this columns of one. Okay, this is my column vector which have one in its rows. Okay. Now and these are my x1 to x6 are my fatty acid compositions. Okay. So this is my x vector. Okay. So the size of x, so we can check what is the size of x. So size of x will be uh, uh, size of x will be 10 cross 6, and since I have added a column of 1, so it will become 10 cross 7. We just go and run till this point. Yeah. Now we can just print x. Yeah. We can check the size also. Yeah. You see 10 cross 7. So I have 10 rows and 7 columns. So first column is column of 1. Okay. This is my x. This is the first column, and the rest are the columns for the different fatty acids. And now this is my y 4 point, which is given. Now this is the formula for the coefficients. Okay. So, if you see here, this is how we write like this is the relation between x and y. So x multiplied by sub coefficients equal to y, and we can find this coefficient using this formula. Okay, x transpose multiplied by x inverse multiplied by x transpose y. Okay, this is what I have done here. Inverse of x transpose x multiplied by x transpose, and this is y4 point. Okay, so this will give me the coefficient. In Octave or in MATLAB, you can directly, instead of doing this, you can directly write this command here, x, this front slash and then y4 point. It will give you the same answer as this one. Okay, let me go run till here. Yeah, now check what is the coefficient. Yeah, so these are my coefficients. Okay, first one is a constant term minus 34.4.62, and the rest are the a1 to a6. Okay, so once I have this, now we can find r2 value to see how good is the fit. Okay, yeah. So for R2 calculation, we know that the formula for R2 is 1 minus S residual upon S total, and where S residual is found like this, which is summation of yi multiplied minus, this is my fitted value. Okay, I think uh, Pradeep, can you mute your mic? Okay. Okay, so my R2 value is 1 minus S residual upon S total. So S residual is summation of uh, square of my yi minus this fitted value. Okay, and S total is summation of yi minus y estimated square. Okay, and this can be directly found as n minus 1 multiplied by variance of that data. So this is what I have done here. Okay. Yeah, see this value. Yeah, so you can see the R2 value. It's 0.97. It's almost like close to 1. So I can say, okay, this is like a good fit. We can also calculate R2 adjusted. Okay. So here I had 6 fatty acids and 10 sample size. So I can calculate the R2 adjusted as this. This formula also the Professor Goodin in his talk showed us. Okay, 1 minus n minus 1 upon n minus p multiplied by 1 minus R2 value. Yeah, so this is my R2 adjusted. This is actually quite big. It's supposed for a good model, this should be like low. Uh, I think almost near to 0.2, 0.3, something like that. Because we had 6 fatty acids and only 10 samples, maybe because of that. Okay. Okay, so this problem is complete. Okay, so I had fatty acid compositions and I wanted to fit a straight line for a physical property, 4 point. Okay, similarly we can do for cloud point, flash point, fat point, and in future if somebody give me some fatty acid composition, then I can predict the property. Okay, so this was one problem. Okay, let me move to second problem. which we have taken from this paper. Okay, I will explain the problem first. So here I have two different kind of crude oil. Okay, uh, and so we have two different kind of crude oil, and we are asked that, like, in market there is a demand for, let's say in market there is demand for certain crude oil which had certain specifications. Okay, and we are receiving two different type of crude oil. So the manager will ask, like, in what ratio should I blend this crude oil so that the resulted crude oil will follow my market demand. Okay, so let's say this is the specification, crude specification for my like required mixture, blended mixture, and these are my two crude oil. So whose TVP data is given. Okay, true boiling point data is given. So the question is, in what ratio should I mix these two crude oil so that I will get this crude oil have following this property. Okay, so this is my desired property, and this is my given crude oils. Okay, okay. So the objective is to find the ratio in which the volumetric ratio in which we should mix these two crude oils so that I will obtain this. Okay, this is my objective here. So in the paper, it is given that that this TVP data, true boiling point data, and this volume fraction, they follow certain relation. Okay, so this is the relation which they follow. Okay, here Ti is the true boiling point, and Xi is the volume fraction, and these are different terms. Okay, so so uh,
बेबी इधर देखो पापा को बेबी बेबी
uh, can I mute him?
Yeah, Pradeep, can I request you to please mute yourself? There is some disturbance coming from your side. Let me see if I can mute him. Yeah, I have muted him. Om Prakash, you can go ahead. Yeah.
So, so my true boiling point and volume fraction, they follow this relation, and it is given in the paper that if we convert, so we can, so we have, so my y is a function of true boiling point, which is given here, ln of Ti minus T naught upon T naught, and T naught is a constant here. It's the initial boiling point, which is known to us in Kelvin. So y is my is function of my true boiling point, and x, my predictor, is function of my volume fraction, which is again ln of upon ln of 1 upon 1 minus xi. Okay. So if we convert my volume fraction in this way and my true boiling point in this way, then from the paper we know that they follow this linear relation, y equal to c1 plus c2x. Okay, and then it is also known that when two or more crude oil, the condensates are mixed together, the linear equation of the mixture, my blended mixture which is desired, is summation of the linear equation of each condensate. Okay, so this is my y, which is uh, true, which is this y, this y, ln of this thing. So this y is equal to summation. There it's a mixture of both the all the components. Okay, they are multiplied by this alpha. This alpha is the blending ratio which we want to find, which is the objective of this problem. Okay, so here, so this we can find y equal to mx plus c for one of the crude oil. For one of the crude oil, this is for the second crude oil, and this is for the mixture. Okay, and from this relation we can see that if we add all these terms, so this alpha j multiplied by m, so that will be if we equate if we add this with if we multiply alpha with this first one and alpha 2 with second one, and we add it, So my slope of the resultant mixture will become this MAB equal to alpha A multiplied by MA plus alpha B multiplied by MB. So this will be the one of the equation, and we know that the sum of alpha A plus alpha B should be equal to 1. Okay, so my ratio, and this alpha is my blending ratio. So this two, using these two equation, we can find this alpha. So first we have to find this M slope MA, slope MB, and slope MAB. Okay. So this slope, this C2 we have to find for each of this crude. My two input crude, and this is the crude which is the mixture crude. Okay. So my objective is to find first C2 for each of them. Then we can find this alpha. Okay. So this is the problem. I hope this is clear. So I'll show the code here. So first thing, we'll write the what is known to us. So my TBP is given and cumulative volume percent. This data is given. Okay, this is X and this is Y data. So you see here. So for this this crude, okay, I've written here. So this is my volume percentage: 10, 30, 50, 70, 90, 99, and this is my TVP corresponding to them. Okay. Now in the paper it was given that this temperature should be in Kelvin, but here these were in Fahrenheit. Okay, so first we have to convert that. So so these are in Fahrenheit. Okay, so first we converted that in Kelvin using this formula. Okay, Fahrenheit minus 32 upon multiplied by 5 by 9 plus 273.15. Okay, so this became in the Kelvin. Okay. Similarly, we did that exercise for crude 2. Okay, second crude. So this becomes in Kelvin. Now we will find this y. Okay, this y which was the function of my true boiling point. Okay, and then we'll find x, which is the function of volume fraction. Okay, so you see here, and this T naught, as I said earlier, is a constant which is given to us. It's the initial boiling point in Kelvin. So this T naught is given for 29.15, and now we can find this y. Okay, y log of my Ti minus T naught upon T naught. Okay, for all 6 of them. I have 6 rows. Okay, I have 6 points here. 1, 2, 3, 4, 5, 6. So I have my y. Now I will find x, capital X, which is function of my volume fraction. So again, I have this log. So this log is ln in octave or in MATLAB. So ln 1 upon 1 minus xi upon 100. Okay. So this is my capital X. Now I have my capital X and capital Y, and we know that they follow this linear relation. So we can use a command from Octave, which is Polyfit, and it will give us the coefficient by C1 and C2 directly. So in earlier problem we manually did it, like we first include a column of 1 for C1 and then C2, and then we use that formula and calculated it. But you can directly find that using this toolbox, this function Polyfit. It just it takes the x value and y value. This is my x value and this y value. And one means I want to fit a linear curve. Want to fit a quadratic curve, you can write here 2, 3, 4, 5, like that. So PA will give us the coefficient. So it will be a vector, column vector. The first element will contain the slope, which is C2, and second element will contain the constant of C1. Okay. Instead of this, you could have done this also, where you just write the x value and then you introduce a column of ones, and then just you use this operator. So both are same. So we can just see what is PA. Yeah. So PA1, this is the slope. Okay, C2 value, and this is the C1 value, the constant term. Okay. So this is my slope. I have the PA1, and this is the constant term, the C1. Okay. Same thing I want to do for the second crude oil. Okay. So before that, I also calculated this R2 value. Okay, it's same as the earlier one. Yeah. So this is my R2 value, 0.97. Here I have plotted the fitted curve. You can see. Yeah. So you see, I had six. This is my straight line. This is the equation. My C1, the constant term, and this is the slope, minus 1.055. Okay. The same thing, the same exercise I have done for the second crude. Okay. First, first I computed. First, I compute the y value. Okay, which is ln of this. Okay, this is y value. Then I compute x value, capital X value, which is function of my volume fraction xi, and then again use the polyfit to compute my slope and my intercept. So again the same thing, I have calculated the R2 value, and then I have done the plot. Let me run till here. Yeah. Yeah. So let me break it. Yeah. So this is the fit for the second crude one. Okay. So I need this slow value, this 0.331 for this one and 0.318 for this one to find my blending ratio. So the same operation I will do for my desired crude. Okay. So my desired crude TVP and volume fraction were given here. The same thing I will do again. My this is my TVP. First I converted the TVP into Kelvin. Then I found y function, which is function of my TVP, and then x, which is function of volume fraction. And again using Polyfit, I have calculated this slope. Okay, and this is my R2 value. So once I found my so once I found my slope, which is MA MB for second crude, and this is the first crude, and this is for the blending mixture. I have this relation, and I know this relation alpha I plus alpha b equal to 1. So I have two equation and two variable. Variables are my alpha and alpha b. I can simply solve it and find this alpha. Okay. So yeah. So if you see here, so I have written in a matrix form. These are my two equation. Okay, so you can see the coefficient of alpha A is here 1, and here coefficient of alpha B is 1. So I have this 1 semicolon, second row. Second row, I have coefficient of alpha A is MA and coefficient of alpha B is MB. So I have here, this is MA for first crude and this is for second crude, MB. So I have this matrix, okay. And for the right hand side, I have one here and here I have MAB. So I have one here and this is the slope of blend which is found here. So I have all these slopes I have already found, okay. And I have this equation, so I can simply I can use one function from Octave which is linsolve. It solved a set of linear equation. So you just put here the matrix, the this matrix, okay, and this matrix, and it will give you the solution. So yeah, so this is basically R multiplied by alpha equal to S. So this is what I'm trying to solve. R multiplied by alpha into S. So R is my this matrix and S is the right hand side. And I want to find alpha. Okay. So let me see. Let me run it. Yeah. You see alpha is given here. So it's 0.1 and 0.1. It's mean that I want to mix 0.81 percentage of first crude and 0.18 percentage of second crude. These are volume fraction. Okay. The point. See if I want to make like if 1 liter is the reference, then I can mix 0.8 liter of first crude and 0.1 liter of second crude, and I will get the desired property of my blending mixture which was required. Yeah. So here we saw like the uses of this function polyval, okay, polyval, and then linsolve to solve linear equations. Okay, polyfit. Yeah. So yeah, this was for the linear regression part. Yeah, sir, are you there?
Yeah, Prakash, I'm there.
Yeah. Yeah. So yeah, I have this one list.
Okay, so any questions for Om Prakash? So what Om Prakash showed you basically is the basic things of regression. When you given y and x data, you can estimate the parameters. Again, if you go back to what we did in terms of sample statistics yesterday, okay, if you want to relate what we talked about when we talk about statistical inference, what do we want to estimate? We really want to estimate the true slope and the true intercept. What does it mean by true? If you had really, let's say in the first problem, where he was trying to predict the, I think trying to predict the 4-point, was it, Om Prakash, in the
4
first
point,
problem?
yeah.
4
Yes.
point, right. So 4-point was a function of various properties with some coefficients. So if I had all possible biodiesels with me, then if I could fit a line for that, really that is like the true, the true parameters you can say. We don't have all possible data. We have a sample, and from that we are estimating. So what we are estimating is so the sample statistics. So the estimated parameter and slopes are really the estimates of the unknown true slope and intercept. Okay. So of course rest is like R square, etc. We'll see whether your fitted model is adequate or not, or whether you want to add some terms, etc. Assuming that your model is correct, you're trying to estimate the true parameters based on computations on a limited data size. Any questions anybody has on this? Okay, if there are no questions, I will take it one step further. Om Prakash, can you stop sharing? Yeah, what I will do is I will just take it one step further and just try to connect with what we did yesterday. If you in the second session yesterday, if you recall, or first and second session both, what we said was whenever you are computing. So what Om Prakash showed you in terms of terminology, what do we say? His slope and intercept estimated values. These are what? These are point estimates, right? These are point estimates of the true slope and the true intercept. Just one single number he's telling us. Okay, so remember we said x bar is a point estimate of mu when we were talking of trying to estimate mean of a population. Same thing he's doing here. It's exactly the same setting, similar setting. What he has got is a point estimate. Yesterday we said, look, point estimate is good, but don't want to stop there. Also want to give me a confidence bound on the true values. Okay, so that I'm sure that the true values, I can say that the true values are in this bound with high confidence, right? So in regression also you can do all of those things. I'm not sure how much Professor Goody was able to cover anyway in a limited time, but what I will just show you is another example where in the code I have done all of those things. The exact method and all can be followed. It's there in any standard textbook on regression. But this idea that whenever you are estimating a parameter, it is beyond just giving a single number as an estimate. You can go more than that. You can give a confidence bound. You can do hypothesis testing on the parameter. All of that holds. What we did yesterday for mu, all of it also holds in a regression context. You can do hypothesis testing on the true slope or the true intercept. You can give confidence bounds on the slope, intercept, various coefficients. You can do that. Okay. So what I will just show you is another example. Let me share my screen. Yeah, I hope my screen is visible.
Yes, sir.
Yeah. So I have another example from regression. It is a problem where we are trying to relate the mileage of a car to the size of the engine. Okay. So it is data for some actual cars taken from some reference. So there is mileage is given to us in terms of miles per gallon. How many miles per gallon does the car run? And the engine displacement in inch cube for various cars. And we want to see this y as a function of x. X is your displacement and y is your mileage. Okay. So simple regression model, y equal to mx plus c. Okay, and I will now show you some data that we have for this. Just give me a second. Yeah, so you can see this Excel sheet. This is the data we have for various type of automobiles. I think this is an old data. I actually do not know whether it is true data or it is manufactured data, but it's taken from some reference. But you see, this is the Y values we have, the mileage, miles per gallon for various types of cars. And this is the corresponding engine displacement, column X1, okay, in inch cube. Ignore the column X2 for now. So we have data about of about 32 cars, right? And we want to see whether Y is a function of X or not using regression. So I'll just show you my code. Let me go to my Octave window and I have the corresponding code. You should be able to see my Octave window. So I have this data over here. The first column is Y and the second column is my the engine size, engine displacement X. And I am going to do fit a regression model, same thing as what Om Prakash did. I'm constructing this matrix X, capital X. The first column of ones corresponding to the intercept. Second column is your engine displacement. And these are estimated coefficients beta hat, X transpose X inverse, X transpose Y. Okay? That's the formula Professor Goody might have talked about in the morning. Or this backslash command in Octave or MATLAB does exactly the same thing, X transpose X inverse, X transpose Y, right? So nothing new here. So far, what is the big deal? Additionally, what you can do is, okay, what is the new thing you can do is, you can also, these are your estimated parameters. You can say what are the variance of these estimated parameters. Remember, yesterday we talked about x bar is an estimate of mu, variance of x bar is sigma square by n, right? Sampling statistics. So this is sampling statistics, sample statistics, beta hat, estimate of true beta, variance of beta hat also we can compute. Okay, so that variance of beta hat is also computed. Once I have that variance, I can get a confidence interval on the true parameters because I assume certain distribution of beta hat, certain density function, it is Gaussian, okay, or it is, there is a related density called T density when you do not know the variance upfront and you have to extract from data. So whatever it is, the point is, you can again, if you can figure out the density function of these beta hats, you can again do confidence interval on the true parameters. So let me just run this code and I want to show that to you. Okay, so what I have here is, what is it plotting? Let me just see. This is just the X matrix. Yeah, it has plotted the X matrix. These are my estimated intercepts and slope. Intercept is 33.72 and slope is minus 0.047. Again, these are what? These are point estimates of the true intercept and the true slope. Okay. If I go down further, this is an estimate of my noise variance, of the measurement noise variance. And these are the estimates of the variances in my estimated intercept and variance in the estimated slope. Equivalent of sigma square by n, which we did for x bar. Same way I can talk of variance in intercept and variance in slope. These are estimated quantities. The true intercept, true slope is a constant. There is no variance with it, but I don't know it. Okay, but my estimate has certain variance. If I were to again generate experimental data, let's say for those cars which had the fixed engine displacement, if I take them out for a drive again and I find out what is the mileage they gave me, this time the mileage numbers will change, right? So my estimated intercept, estimated slope will change. So there is a variability shared with them. They keep changing. They are random variables. Okay, so these are the variances. And now, as I said, if I assume certain distribution which one can derive for these beta hats, then you can use that to construct confidence intervals on the true intercept and the true slope. Okay, so this is what has been done here. A 95% confidence interval on the intercept is this. 30.774 is the lower value, 36.672 is the upper value. The point estimate is 33.722 and you are 95% sure that the true intercept is in this range, 30.77 to 36.67. Okay, smaller the interval, the more accurately you have estimated the truth. This point estimate is an accurate estimate if your interval is small in width. This for the intercept, same way I can do for the slope. Slope, you see, the point estimate was minus 0.047. The interval, 95% confidence interval is this, minus 0.0569 to minus 0.0377. That's a likely range in which the true intercept lies. Okay. So whatever was done in statistical inferencing, all of that carries over when you're doing regression, for example, because whatever you're estimating from data is noise corrupted. That causes randomness in the data. Okay, that's how we think of data as a random variable, whatever we are generating, because if you repeat the experiment, data changes, right? The model is, the assumption is the truth is not changing. It is only the way we're generating data, the way we are doing the experiments, the way we are collecting samples, that is causing the data to change. It's like we're generating samples. Every time we get a different set of samples. Okay. So we can get confidence interval on the slope also. We can do hypothesis testing. Is the true slope equal to 1, not equal to 1? I can do that hypothesis testing. I don't have the results here, but you can do all of that. Is the true slope greater than 1, H naught? Alternative hypothesis, it is less than 1. Okay, all of that you can do at a certain significance level with specified value of alpha. So all of that carries forward. Okay, and something more I want to show you. In fact, that is when we use. So what do we do with this? We got the confidence intervals on the intercept and slope. So what is the big deal? Finally, when you go back, you have got a model. You have got a model with these values, and you can use that model to make predictions, right? What's the purpose of the model? That tomorrow you will give me a new car which has not been tested. You will tell me its engine displacement, and you will say, okay, now what can I say about its mileage? So I will use the model that I have to predict what that mileage will be. Now again, you can ask the question, what was the prediction? That predicted value from this line, okay, is just a point prediction. Can you again give me a confidence interval on that prediction? This is my point value prediction, this is my confidence interval. It turns out, yes, you can do that. Okay, let me first just show you in my slides what is the question which was posed. Okay, so that is what this says, that one of the main use of a regression. In fact, the question that was asked to Om Prakash, how do you get the Y data? So the Y data on which he obtained a model, okay, based on which he obtained a model, that was the training data, that was the experiments he has done. But now finally, what is the use of his model? He will take his model and predict Y value for some new biodiesel, right? So it's a prediction. That's the whole purpose. That's one of the main purpose of having a model. You can predict what will happen in future when you encounter a new scenario, new situation, right? So in this engine displacement problem, this slide says that one of the main use of such a model, regression model, is for predicting behavior for a scenario without having to conduct experiments. I get a new car, I don't want to drive it, or before buying a new car, I just look at the specifications of that car. Oh, what is the engine size, engine displacement? For example, a company intends to build a new car with engine displacement x equal to 200. Then it would be interested in predicting the value of the mileage. What would be the mileage? Since there is no prior data available for car with x equal to 200, the regression model we have developed can be used to predict the mileage, right? And whatever intercept and slope we had, so intercept plus slope into 200 gives me the predicted mileage, and that turns out to be 24.33. okay, what is this prediction? This is, again, you can say, is just a point estimate. So this particular slide shows that the plus points or whatever was the data which was available to you, you fitted this line, whatever slope and intercept you obtained, you fitted this line. And now the question is, for if x equal to 200, you don't have any plus point for that, you don't have an existing car, you're saying what would be the Y value. So you go and look at this line and say, what does this line tell you? So 24 point something, that's your predicted Y value. Again, you can ask, is that a random variable? The predicted value? Answer is yes, it's a random variable. What does it mean? If I were to repeat the experiment, if I were to get these new sets of pluses, again run the existing cars, I will get a new set of pluses from which I will get a different straight line. And from that straight line, if I again predict at 200, I will get a different prediction, right? Because now our estimated quantities are based on data, predictions are based on these estimated parameters. Predictions are also random variables. Can I do the same thing again? Can I say, give me a point, not just this point estimate, not just this point value, give me a confidence interval on this, a likely range in which the true predicted value will lie? Answer is, you can do that also. Okay. So I will just show you in my code. In fact, there are two things we can do. So again, we have not covered this theory in any particular module. So don't worry about it. But I just want you to take this message with you, that when you deal with experimental data or any real data, don't stop at computing the point values. That's just the first step. Okay, and you have to go beyond that, be able to give valid intervals. And that's the practice. Experimentalists know that. Plus minus something they always give, some error bar. So what is that error bar? It's essentially a confidence interval you are giving. Okay, that the true value could be in this range, even though what I'm showing you is some number, right? So there is fundamental, there is formal basis for it, a very strong basis for doing those things. And those error bars, what do they mean? They depend on the the significance level. They represent a certain confidence interval, 95%, 99%. Accordingly, the error bars will change in width. Okay, so those sorts of things you have to remember. Yeah, and you have to use to the extent possible to to have good, meaningful data analysis. Okay, so these were the confidence intervals on intercept and slope. I have come back to my code, the output of my code, and if I run it again, what did it give me here? Yeah, standard errors for the mean response. Okay, I'll just explain. And this is confidence interval. Let me show you in the plot. I think that's better. Oh, there is waiting for my inputs. So let me just take you. Yeah, so this is the plot which I have generated. I hope all of you can see it. What in the slide you were seeing as plus points, here these are x points. What are these? X points is the given original data, the engine displacement and the corresponding gasoline mileage. We fitted a straight line, the one in the center, this orange line in the center is our fitted straight line. You see these red curves now, okay? And you see these black ones. Let me talk about the black one first. What is the black one? We said at 200, if you want to predict, if I make a new car at x equal to 200, what will be the y value? So you go to 200, you say, oh, what does your line predict? This is your line, the middle one, the orange one. You go and look at the y value. It is around 24 point something. Now you ask, if I were to get a new set of data of these crosses, I get a different line, my predicted value will change. So what can I say about the true value? True predicted value is the same for x equal to 200, but your truth is same, but your estimate is changing of the predicted value, right? So you don't want to stop at this point estimate. You want to give a confidence interval. So what you see, this black line, this is really the confidence interval. You have 95% confidence that the true mileage for x equal to 200 will be between this value, maybe around 18 to around 31. This black line is the width, lower bound, upper bound. For any x, you can generate this lower bound, upper bound. Okay, you can give this prediction interval. Yeah, so when you use a model, don't just predict and give one value and stop there. Also say how good or bad your prediction is by giving this prediction interval. Okay, and it is not very obvious in this. Okay, let me talk about the red one also. The red one is a related quantity which says that if you were to do okay, red one, let me not worry about. This is something called as mean response, but it's a related quantity. Again, you're doing some interval. Let's look at the black one only. It's not very obvious from these curves, but if you zoom in closely, if you could zoom in closely and see it, you would see that this width of the confidence interval, the top black, the value from the top black line and the bottom black line, that is the width of the confidence interval. As you vary along the x direction, the width changes. It is the smallest in the center in the average value of x. You have data in some range of x going from 100 to 500. You look at the average x from data set, and this width will be smallest there, and as you move outside, the width will expand. Meaning when you're using this regression model to extrapolate, okay, you're going away newer x outside your range which you had for training data, your predictions are going to be more and more inferior, more and more uncertain. The prediction intervals increase. Okay, again, you can do hypothesis testing. What's the null hypothesis? You say, oh, my predicted mileage at 200, you can say the true mileage at 200 will be greater than 40. You can do hypothesis testing of that. Okay? And because your confidence interval does not exclude 40, it is actually below 40. In this case, you will be able to reject that null hypothesis. But whatever we did yesterday in terms of x bar and mu, we just took some sample average and we wanted to estimate the true mean. All of that analysis, statistical inference carries forward when we are doing any modeling exercise, like in regression. So it carries forward for the parameters of that model. It carries forward to any quantity that you compute using that model. So there is always a notion of that there is a true quantity and there is your estimated or predicted value. And those are like point estimates of the truth. So you of course compute the point estimates, and you also try to quantify a likely range, confidence interval on the truth. Okay? At least when things are like models are linear, things are well behaved, so to speak, densities are Gaussian, error densities are Gaussian. These things are can be quantified quite accurately. Okay, there is standard theory available for it. When your models become more complex, okay, when you're doing data processing, which is so this is what you're doing is linear regression. When you go beyond linear regression, more complex data processing, then many times analytically these things cannot be computed with confidence intervals and so on, but one can still carry over these ideas. Yeah, so this is what I wanted to just impress upon you, that whatever statistical inference we did, the preliminaries of statistics, okay, that is useful when we want to use a data derived model for any purpose. Okay, if the model had been based on our first principle understanding, what we say physics based understanding, okay, supposing I knew that this y has to be equal to x, some other y, let's say not gasoline mileage, something else, flow rates, I said flow in, flow out. I know that flow in has to be equal to flow out. If I fit a straight line, the slope has to be 1, intercept has to be 0, right? This is based on physics. There is no, I exactly know the true slope. Okay, but that's not the case. I do not know the true slope. I'm just trying to extract it from data. And there will always be uncertainty when you extract things from data, even if because you are working with a small sample, finite sample. So you have to keep it at the back of your mind that these things come associated with data, that sampling statistics, that there are there are uncertainties, there are errors, random errors. So whatever quantities you compute from data, they are not perfect. Okay? So you always have to keep looking for these sorts of intervals. Yeah. So any question on this? So in fact, I am not sure. Let me just see in my slide if I have some numbers. I can show that to you. Yeah, so it's the same thing. It is saying this feature response. So yeah, so this is the feature response. So x equal to 200. I have my confidence interval is this 17.9 to 30.8. Okay, point value was 24 point something, but a likely range is 17.9 to 30.8. Okay, so that's your interval. So now you are sure. Now you can do hypothesis testing. Is the true value greater than 15, equal to 15, not equal to 15? All sorts of things you can do. Okay, this is a 95% confidence interval. Okay. So the last point is important here, that we can systematically quantify the uncertainties associated with model-based predictions. Okay, at least in these nice settings when the model is linear in the parameters. Okay, yeah, I think that's all I have for regression. Any questions anybody has? No questions or comments? Okay, let me just go back to screen. I'll stop sharing. Yeah, nobody has any questions? What's the time? Let me just see the time, how we are doing in terms of time. So we have about 15-20 minutes. So what I can do is, there is no question, I'll just take you to the data, through the data reconciliation which I talked about in the morning, some codes I have. Okay, and I'll just illustrate through again simulations some of those cross error detection ideas. Okay, and the results that I had. Let me just open my codes. Okay. This is a basic data reconciliation code. I showed that in the morning today. Let me open my file also. Let me see if I can open my file. So recall we had this flow problem, okay, and we had these measurements and we wanted to reconcile them. And what I have done is simple written a code. We actually got the analytical solution. This was our problem for this flow problem, getting these x tildes, and we had an analytical solution for x tilde and the corresponding covariance matrix. So that is one code. Maybe I'll skip that. I'll go to the gross error one. Okay. Yeah. So the gross error, let me show you, that is probably more interesting. In this flow example, yeah, this example, what we did in this example was we added some gross error to one of the sensors, some fixed number, and then we want to see whether we can back out two things. First, that there is at least one sensor which has a problem by looking at some weighted sum of squares of these residuals. Okay, if that exceeds some threshold, we'll say at least one sensor has a problem, because noise variances are certain magnitude. Based on that, I know that the strength of the residuals should be less than some threshold. I can put some threshold. And second, we also want to identify which sensor has a gross error. Okay, so it is related to what Anbumati asked. So if we have a model, Anbumati's question was, no, how do we in a data set, in large data set, how will we do these things? So here, of course, we know the model. So you give me any data, I can figure out whether there is a faulty sensor or biased sensor or not. Okay. This model is coming from first principle, from physics. It is not a data-driven model. So I don't depend on data for writing down my flow balances. Okay. For now, I'll just show the code where you will see this detection behavior or performance. So, okay, let me open the other one. In fact, let me do this gross detection multiparalyzation. So it's the same A matrix which I had shown you in the morning. True flow rates, 140, 60, 60, 100. Noise variance. You generate the measurements by adding that random noise, which is Gaussian distributed. This n gives you Gaussian distributed random numbers. Okay. Now you add a bias of magnitude 10 to second sensor. 10 or 15. In the slide it was 15. We can make it 15. Let's see 15. And what happens? And you want to see whether you can detect whether there is a bias or not. That this is the code which does that, and then also tries to figure out which is the sensor which has the bias. Okay. The only additional thing I'm doing is I'm doing this experiment many times, 100 times. 100 times I'm generating the measurements. The true value is not changing. X true is the same, but measurements keep on changing. You every minute or every half an hour you go and measure your flow rates. The true flow rate is the same, but your sensed value changes. Sensor shows you different readings. Okay. What is same is that every time the second measurement has this additional 15 added to whatever its value was, right? So and now you apply this procedure. Can you figure out how many times out of 100 can you figure out the correct sensor and also get an estimate of this bias? You know the truth is 15. Okay. So there is again formal theory. It's related to that hypothesis testing, whether there is a bias or not, and which sensor is the most likely culprit if there is a bias. All of this is in a hypothesis testing framework, which we did yesterday. And again, remember, there were type 1 and type 2 errors. There is no bias, but you still say a bias, type 1, or there could be a bias, you still miss a bias. So all those errors occur here also. Okay, that type 1, type 2 errors. Let me just run this code and you will just see the behavior. I hope it's not giving me problem. No. Okay. Yeah. Okay. What you have is this dotted line is a threshold. This gamma is those scaled residuals. So that at any particular instant, you have done 100 experiments. 100 times you generate data, and every time you look at the data, sensor 2 has a problem. And what you're saying in all those 100 instances, every time you said, look, there is a bias in at least one sensor. So you got that correctly. Because why? That bias magnitude is large. At 15 we had kept. Okay. So this is above the threshold. I'll show you the next figure, figure 2. What does it show you? This shows you every time you're also, once you say there is a bias, you try to figure out which sensor is the most likely culprit. Again, how? By looking at patterns. Every sensor has a different signature on that residual vector. So you're saying the current residual vector matches which signature the most. Okay, effectively that, but it's cast in formal hypothesis testing framework. You can build nice systematic way of doing it. And every time you got it correct, so this shows the index of the bias sensor. You said bias is in sensor 2, 2, 2 at all the 100 time instants. Okay, these are, I'm joining them by line, but actually these are like different instants. These are just points. So 100% correct identification. And the figure number 3, you know that the true bias we added was 15. And what it shows you, the estimates of bias for different experiments. Estimates vary, but on an average, they fluctuate around 15. So pretty good estimates you get of the biased value. Okay? So data reconciliation is allowing you all these things. It is allowing you to figure out that there is a faulty sensor and what is the bias in that faulty sensor. And it's doing a pretty good job of it. Of course, the performance, how well it has identified the culprit, how well it has estimated the bias, all of it depends on the magnitude of the bias. As you would intuitively think that if what will happen if I decrease the magnitude of the bias, the fault is there, but it's a very small magnitude fault. If I make it 5 or make it 10, what do you think will happen? If I run the code again, my performance will go down. I will sometimes start giving wrong identification, start getting wrong identification, right? Let me run it at 10. What happens? Let me just see. Okay, this first one, 100 experiments you have done, and when the blue is below the dotted line, at that point you're saying all sensors are okay. You're rejecting the null hypothesis, that you're accepting the null hypothesis that there is no gross error. So the many time instance you will not think that there is any culprit sensor. When you think there is a culprit sensor, sometimes still you don't get the correct culprit. You get 2 estimate, you identify 2 to be the culprit, sometimes you identify 4 as the culprit. Okay, so that is the wrong culprit you have caught. You cannot, because there is always a question of probabilities. Then you're generating random numbers. Sometimes it's below some threshold, sometimes it's less than some threshold. Only you can say these things with that alpha, 95%, 99% probability, etc. You can pre-compute those type 1, type 2 errors, that will hold. But there is always a 5%, 10% chance of getting a wrong result. Okay. Here the estimates of the bias, sometimes you even get negative estimates. Of course, you have got the wrong candidate, you even get sometimes negative estimates of the bias. The true bias was 10. Yeah. So it of course is a function of the magnitude of the error. Larger the error, actually the easier it is to catch it. Small errors, subtle errors are more difficult to catch. If there is a small deviation, 1 unit in my sensor, how will I ever figure it out when on top of it there is noise in the sensor, noise in other sensors also, right? I can't figure out that there is a miscalibration of 1 unit in my sensor. My weighing machine always shows me 1 kg more than the actual weight. I can't figure out, because anyway there is so much noise in the weighing machine. When I stand it, my weight keeps on changing, right? So yeah, so one can do those experiments, increase the bias or decrease it and so on. But again, the whatever we did in terms of hypothesis testing, okay, thinking of data as random variables, all of that has is the techniques, is the foundation, the building block for this sort of analysis. What is analysis? You have data from process, from your system. We are saying before I use data for any control or any further making some inferences, like, oh, based on this data, I think this catalyst is better, this catalyst is worse. Before I do that, I try to reconcile data. because my sensors are always noisy. Sensors could also be faulty. So let me not use the raw data as it is. If I have some understanding of the process, let me see if using that understanding and the data I have got, can you make some inferences about the data? Okay, can you identify some bad sensors, bad readings, outliers, for example, these sorts of things. And then I get clean data, I work with it. Okay. Post this session, the last session, you'll also see, we'll talk about principal component analysis, where hopefully time permitting, I'll also show you how model itself can be obtained from data in the first place. If I don't have physical knowledge of the model from physics, I can extract the model from data. But as Anbumati had rightly pointed out, that is under the assumption that whatever that raw data is, that is free of such biases. Okay, otherwise I will have problem. So I get clean data in the sense of not having biases. Random errors will always be there. I am okay with it. I can handle it. We can live with it. But there are no biases in that data, and from that data I identify model, and now in future I can use that model to say something about the data that I am getting. Okay. So are there any questions? Okay, let me stop sharing. So if there are no questions, then I think we can break for some time. No, if you're in, I don't know if what is it that our TechWhip organizers have told you about the notes sharing, but we can share all these codes and slides with you, and you can look at it, play with it, and if you have any questions or comments, even after this course, you are welcome to get in touch with me. Okay. Okay, then I think let's take a break. So we'll meet at 3:45. That's when our last session starts. Okay. Thank you.